My paper is called Score-Based Generative Modeling Through Stochastic Differential Equations, and it is by Yang Song and these other authors, and there's the link. So what is the goal of this paper? The situation is that you have some data x naught, which comes from an unknowable underlying distribution px naught. And you want to use the data that you have, the observations, to learn about the underlying distribution so that you're able to generate more observations from it. So an example of this could be x naught is a bunch of images of cats. And there's an underlying distribution that produces images of cats, but you don't know what it is. But you want to learn it so you can produce more images of cats. Or another example could be x naught is sentences of poetry. You can't know what underlying distribution is producing these sentences of poetry, but you want to generate more sentences of poetry, so you need to learn about it. So how can you use your observations to learn about the underlying density? Your first instinct would probably be to just learn directly about it. Try to use your observations to learn what you can about the density that produced them. But the problem is that carries with it a pesky normalizing constant that makes it more difficult to work with. For this reason, it's better to work with the gradient of the log density. This is a better quantity to try to estimate because it does not involve the normalizing constant. And that function is called the score, the gradient of the log density. So say you did know the score. How could you use that to get samples from the underlying distribution? You could do it using this algorithm. So start at x naught, which is your initial value. It can just be a draw from a normal or a uniform, whatever. And you will move according to the gradient. So bump along according to the gradient, and then also an additional bump from a Gaussian. And so at first you're bumping a lot because E is the largest it's ever going to be, epsilon. And next bump will be smaller, and then smaller. And so you're bumping along according to the gradient until eventually epsilon goes to 0 and you have stopped moving. When you stop moving, you will have arrived at an observation from the underlying distribution. So let's demonstrate that for this true scenario. In this scenario, we have a mixture of two univariate Gaussians. And in this case, the gradient can be calculated analytically like this from that distribution. So here's how you implement it in code. You can see we have our epsilons. They are shrinking as you go from I equals 1 to k. They are shrinking, getting smaller and smaller. We have 10,000 for k. It's supposed to go to infinity, but we just did 10,000. Here's our initial guess, just the uniform. That's what we start with. And then we do those bumps. And we do bump, 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 bump. And when we stop, we obtain a sample from the underlying distribution. And so you do that a bunch of times and you obtain a bunch of samples, and it looks like this. So it did. It matched the true underlying distribution very well. So we see that it works. So now we're convinced that if you know the score, it can help you get samples from your underlying distribution. But of course, we don't know the score. All we have are these samples x naught. So we need to use them to learn about the score. And how are we going to do that? We are going to take our observations x naught and we'll add increasing amounts of perturbation to them. And here's the exact formula for doing that. When t is equal to 0, that's the minimum amount of perturbation corresponding to sigma minimum. When t is 1, that's the maximum amount of perturbation corresponding to sigma maximum. And then for t in between 0 and 1, you will be gradually increasing the amount of perturbation in an exponential fashion. And so this is going to help us, and you will soon see why. So let's see how adding this perturbation is going to help us figure out the score. This s is our function. It is our attempt to learn the score. So we want it to learn the score well. It needs to minimize this mean squared error right here. But as written, this mean squared error, we cannot evaluate it because it involves the truth. We need to do some simplifications. First one, we use the law of total probability. Next one, we use the conditional probability for this perturbed version given the initial version. And then it helps us rewrite the score as this expectation, which is already an improvement in terms of being something we can actually use. Now we can simplify our attempt at a loss function by plugging in this new version of the score into the old version, and we get this. We elaborate some more, and we get this. But we can also not evaluate this, because this expectation out here is with respect to the true underlying distribution and the distribution of the perturbed. We don't know either of those. But we can use a Monte Carlo estimate, like this. So now everything in here is just either a x naught, one of our observations, or a perturbed version of it, xt. Now why is that a good loss function? The reason it's good is because it was derived directly from the theoretical mean squared error, and we did not use any approximations or inequalities or anything until the end when we used a very textbook Monte Carlo approximation. And so you can train a neural network using this loss, and the neural network will be playing the role of this S, and we will minimize this loss using all of our observations and perturbing them. Let's think about what this neural network S theta is actually doing. So theta are the parameters of the neural network that have to be fit. The two arguments are an observation and t. T tells it how much perturbation has that observation received. So the neural network takes those two pieces of information and then it thinks about what should it output for the score, the corresponding score. So if it receives a large t, it will consider through the loss function that a lot of perturbation has occurred, and then it will think about how it should react accordingly. If it receives a small t, it will think, okay, not much perturbation has occurred, and it will react accordingly. So let's look at a simulated example. Here the truth is a mixture of two bivariate Gaussians. And what's good about this example is if you take the derivative of the log of this, you obtain the truth. That means when we actually go about fitting our neural network, we do everything. At the end, we can see if it did a good job by comparing it to this truth. So this is what the vector field for the true score looks like. You see the bivariate Gaussian, the mixture of bivariate Gaussians. And now a question I had is, why do we have to bother with a bunch of different t's? Why can't we just choose one small t, which means very little perturbation, and use this version of the loss? So then we're already very close to the truth. Why do we have to do a bunch of different t's? So I tried that, and here's what I got. It worked pretty well, but you see in the outskirts, it did not really match the true vector field. So that convinced me that yes, we need to do what Song actually said, which is use a bunch of different t's. We can do better. So we do need this full loss function where we have a bunch of different t's. And we will use this neural network architecture. First of all, the neural network does not like time as a scalar. So it turns it into this embedding, which uses normal random variables w, and it uses sines and cosines to turn scalar t into a vector. Then we move through 6 layers of the neural network, and at the end of the training it will output it will be optimizing the best guess at the true score. Now let's see how it did. Here is the score, the true score, when we have a lot of perturbation, t is equal to 0.9, and we see our estimate is very close. Here is a little less perturbation, so the data didn't get perturbed as much. We still did very good. Here is barely any perturbation. This is very close to no perturbation. And we did decently well, better than the previous one I showed you, but it's not perfect, but it's pretty good. So now that we have a nicely trained neural network that matches the vector fields well for the different t's, how are we going to use it to get samples? First, we'll go over the discrete way. So we will choose a discrete grid of time points, 0.99, 0.98, 0.01, and we will start out with an initial draw from the domain, and we will perturb it by a large amount. So T1 corresponds to a large amount of perturbation. And then we will use that algorithm that we saw from the univariate Gaussian case previously. Remember the algorithm that it used to have the true score here, now it has our neural network score. And it has the neural network score corresponding to T1. So that was that large vector field that we saw. And we move around according to that vector field until epsilon has diminished down to 0. And then we stop moving, and now we're done with that vector field. And we have stopped at a new location. Now we're at that new location, and we add a little bit less perturbation to it. And then we move around from that point according to the vector field which corresponds to a little less perturbation, that one that was a little less egg-shaped. We move around until epsilon has diminished to 0. Now we're at a new place. Now to that new place, we add a slightly less amount of perturbation. And then we move around according to the gradient, according to T3, which is slightly less perturbation. We repeat this until we arrive at T sub m, which means now we are hardly adding anything and we can officially stop. And once you stop, you have obtained a sample from the underlying distribution. So that discrete way is nice, but the problem with it is the way to gain, to improve it would be to choose a more and more dense grid. But wouldn't it be nice if we could just move past discrete and go to continuous? And there is a way to do it. The way is to rewrite this perturbation equation as a stochastic differential equation. So this encapsulates how we are perturbing our x's by Gaussian and by a certain schedule. So this is encapsulating the perturbation, and there is in fact a way to go backwards. It's called a reverse time SDE, and it looks like this. So this is the reverse time SDE. This means you start at the most perturbed point and you move backwards. So this could be solved analytically if this S was actually an analytic expression. But in our case, it is a neural network, so this cannot be solved analytically. You have to use numerical methods. So you integrate over this reverse time stochastic differential equation, and it will, using this numerical method, and it will move you back to a sample from the underlying distribution. So we do that 20,000 times. Here's the truth, and here's what we got when we used that reverse time stochastic differential equation. And we see it did a pretty good job, but in those places where our vector field did not quite match, or our vector fields, since we are in x by t, we do not obtain perfect performance, but it still is a good proof of concept. Thank you.